density log or the Rhob log. Density log is based on the gamma ray attenuation during the moving through the rocks. If we push the gamma rays into the formation, it can interact with the matter with three different mechanisms: photoelectric effect, Compton effect, and the electron-positron appearance. Gamma rays are interacting not with the nuclear, but the gamma rays are interacting with the electrons that are flying around the nuclear. Now let's look how it works in case of the Compton effect. Imagine that we have hydrogen. In hydrogen we do have one proton, and that means that the atom gets only one electron that is flying around the proton. If we are taking, for example, 100 gamma rays and push them simultaneously on this atom, how many of them gonna interact with this electron? Most likely one or two. We don't think that it's gonna be more. If we change the situation, if we take the atom of the ferrum, in this case we're gonna have 26 protons in the nuclear and 26 electrons flying around. If we push the same amount of the gamma rays, we're gonna have much more gamma rays to interact. And in this case, we're gonna obtain completely different situation. So the more electrons in the nuclear, the more the interaction of the Compton. The interesting story is that the Compton interaction shows us the amount of the electron, and the amount of the electron correlates with the bulk density. So finally we can measure the bulk density by using the gamma ray, the emission of the gamma ray. Density log measures the bulk density. Why should we care about the bulk density of the rock? Let's look at one example. Imagine that we do have 1 cubic meter of the water. What's going to be the mass of the cubic meter of the water? It's going to be equal to 1 ton, because the density of the water equals to 1. Okay. Now let's take another example. Let's take another cubic meter, but now it's going to be filled with a quartz, CO2. In this case, the mass is going to be equal to 2.6, because the density of the quartz equals to 2.6. And now let's take the third example. Let's take the same cubic meter, but let's divide that onto 2 equal parts. And the first part we're gonna fill with the water, and the second part we're gonna fill with quartz. What's gonna be mass of that cubic meter? In this case, we got the half of the CO2 that give us 1.3, and the half of the water that give us 0.5. So mass gonna be 1.8 tons. And now let's calculate porosity. What is porosity? Porosity is a measure of the volume that is filled by the fluid. So in case of the cubic meter of water, porosity is equal to 1 or 100%, because the whole volume of this model is filled by the water. In the second case, porosity equals to 0, because we designed that model so we don't have anything except the CO2, except the quartz. And the porosity of the third case is equal to 0.5 or 50%, because half of the volume is filled with water and half of the volume is filled with a quartz. Now let's look at the graph. On the y-axis, we're going to put porosity, while on the x-axis, we're going to put density. And now let's see. In case if we have density equals to 1, we're going to have porosity equals to 100 or 1. That gives us this point. In case of the density equals to 1.8, we're going to have porosity equals to 0.5. That gives us this point. And in case of the density equals to 2.6, we're going to have porosity equals to 0. That gives us this point. So we can see that all of these 3 points actually lies on that line. So we're going to have the linear regression, the linear correlation between density and porosity. That gives us the information about the density of the rock and its connection with the porosity. And the porosity gonna give us the information about the reserves. So let's look at the example. The red line shows us the presence of the gamma ray log. On the second column, the red line shows us the SP log, and the black line shows us the apparent resistivity. On the third column, the green one shows us the lateral log deep, while the blue one shows us the induction log deep. And the final column shows us the Rhob log or the density log. Now let's interpret that formation. On the first interval, we do have shale, because we have the high gamma ray readings, high SP readings, and the low readings of the apparent resistivity and the lateral log deep. In this layer, we have a kind of a clean rock. We have the low readings of the gamma ray, low readings of the SP. Simultaneously, in this layer, we got the high resistivity, both by apparent resistivity and the lateral log and the induction log. So it's a kind of a clean, high resistant rock. And we know that it's either the high porous rock filled with hydrocarbons or simply the rock with a low porosity. And it's quite hard to distinguish by using only these logs. If we look deeper in the formation, here we have once again shale, because it's a high gamma ray, high SP, and low resistivity. And deep in the formation, we have once again low gamma ray, low SP, and high resistivity by all of the readings. So here is once again a kind of a clean rock with a high resistivity. That means either porous rock with a hydrocarbon or rock with a low porosity. And now let's look at the density log, because it's going to have an answer. We see that in this first layer, the upper layer, we have the high density. And on the bottom layer, we got low density. High density means low porosity. That means the first layer, this one, it's a clean rock, but really low porous rock. And on the bottom here, we got high porosity because of the low density. And the high resistivity in this case show us the presence of the hydrocarbons. The main objectives of the density log are assessment of the rock density, assessment of reservoir porosity, and assessment of lithology. The main limitations are the shallow investigation depth, only about 12 centimeters, and the low recording speed.